Okay, so this morning we'll do this year 18-19 Sem 1 paper. All right. I will have to finish at about 1:20 to 1:30 in one and a half hours or so, because I have to leave for another meeting. All right, so okay, let's get started then. Okay, again, we'll do the signals first, all the signals question, and then the systems questions. Okay. All right. So question 1 is a systems question. Okay, question 2 is a signals question. So let's start with this question 2. All right, so let W and B be the spectrum and bandwidth respectively of a signal, omega WT. Using WT, we form 3 other signals, as you can see there, X, Y, and Z. Let capital X, capital Y, and capital Z be the spectrum of X, Y, and T respectively. So express capital X in terms of W, that's part A, then Y in terms of W, part B, and then part C will be Z in terms of W, okay? So there are these 3 parts. So as you can see from the question, all right, this is a test of the, again, the properties of the Fourier transform, all right, Fourier transform. So what we see in the first case is that X is made up of multiplying W with this set of exponential terms, right? Exponential terms. So if you look at the Fourier transform table, right? Whenever you have an exponential term in one domain, it means a shift in the other domain. So now we have an exponential term here. It means that you have a delta function in the frequency domain comprising of the shifts. The shifts are all given by the term on the exponent. Y, on the other hand, is scaling. So that's straightforward. Scaling of W. And Z is time shift. So that means on the frequency side, you will have an exponential term. So those are basically those 3 things. Okay. So let's start. So let's take the first one. So we have XT, which is WT, multiplied by this product of E to the J 2 pi KT. 2 pi KT. So if you look at your formula sheet, all right, over here, let me expand that. So you can see that a time shift minus T will give you a minus E to J 2 pi F T naught. So now we have J 2 pi F times K. If you look at the question, J 2 pi KT. All right, KT. So we have this here. J 2 pi F naught is K here. F naught is K. So you will have shifts of F minus K here, as you can see. All right, shifts of F minus K. And delta T give you 1. So if you have if you have 1 here, K is 1, you will get delta F. So you have all the delta Fs. Each of them will be shifted by K. All right. Okay. So that's where we are. Okay. So we will apply that. So XF in that case will be little w become WF. Multiplication becomes a convolution. This guy becomes a, for each exponential term, it becomes a delta. A delta will be F minus K because F naught is K now. All right. So convolving with the delta function means that you are having the replication property of the impulse function. So that means that you replicate WF at F equals 0, F equals to K, F equals to 2K, and 3K, 4 and 5, and so on. Okay, so that means this is summation K W into F minus K. So that's part 1. Questions? Okay, so if no questions, then we go to the second one. So the second one, we are given that YT is W 5T. So in this case, this is straightforward. YF will be 1 over 5 W of F over 5. Okay, this is straightforward. All right, so that's the first part of part B. Then he asks you, determine the bandwidth of Y. Now, what we see from here is that Y will be 5 times of whatever is the bandwidth of W. So if W was bandwidth of, say, 1 Hertz, WF over 5 will be 5 Hertz wide. As an example, okay? So in the question, he told you that the bandwidth of W, which is up here, is B. So Y in that case will be 5 times B. So bandwidth of Y YT 5 will be 5B. Any questions? All right. All right, no questions. Then we go to C. So in C, we have ZT is equals to W T minus 0.5. So there's a time shift. So in frequency, it will be whatever is W with a shift E to the minus J 2 pi F of 0.2. Okay, so that's the first part. Second part is he asks you determine the phase of Z. Okay, phase of Z in terms of the phase of W. So the phase of Z in that case will be the phase of W and the phase of this guy, E to the minus J 0.4 pi F. Okay, we are not told what is phase of W, so we leave it there. So this is still the same. We are not told what it is in the question, but the phase of this guy will be minus 0.4 pi F. Okay, so that's the answer. Any questions? All right, so these are very basic questions relating to your understanding of how to use the properties of the Fourier transform. All right, if not, we go to the next one over here. All right, question 3. So the signal XT shown in figure Q3 is sampled at a sampling frequency of 0.5 Hertz to give the sample signal XS. Obtain the expression for XT. Okay, so that's the first part. And then find its Fourier transform. So you can see that XT consists of a rect, as you can see here, a rect, a tri, a big tri, and then you have a small tri to minus to get the flat top. That's right, 2 tris, okay? So that's what it is. So it's relatively straightforward in this case. All right. So we can see that XT has a rect of height 1. It's a rect of height 1 and a width of 6 minus 3 to plus 3. So you have a rect T over 6. Then you have a big trie from minus 2 to plus 2. From minus 2 to plus 2. And you can see that it goes from 1 all the way to 3. If you extend the line, if you draw the line, 1 to 3, that means it's a height of 2. 3 minus 1 is 2. So you have a trie with T over 2. And lastly, you have another trie that you need to subtract of height 1. Okay? Minus a trie of height 1. So those are 3 parts. So now if you take the Fourier transform, XF, red will give you sinc 6, sinc 6F. This trie will give you plus 2 times 2 will be 4, sinc squared 2F. And the last one will be minus sinc squared F. All right. Any questions so far?
Prof. Check with you. For the second triangle, right? How we know the height is 2? Because it's out of the skew already.
You draw up lah.
But because it can be 2.5, it can be 2, it can be 3.
You can take a ruler and measure it later. You draw a line up here, draw a line up here, draw a line up where they meet. You go from here to here. You measure how many millimeters is this. From here, how many millimeters you find is the same.
Oh, so this is the actual skew as per the ruler lah.
Yeah lah.
Oh, okay. Okay, thanks.
Huh? All right. And any other question? You know your ruler here, right? You got a millimeter here, you millimeter over here. You just measure, you know. All right, yeah. All right. The last part is derive the Fourier transform of the sample signal. Now, traditionally, we would say that the sample signal. Traditionally, we say that the sample signal is the original signal multiplied by the sampling cone function. Right? Traditionally. All right. But notice that this is a limited pulse. Okay, a limited pulse. So what happens when you sample it, okay, and you're told that the sampling frequency is 0.5 hertz. That means TS is 2 seconds. TS is 2 seconds. So if you sample this guy and apply this, you will get another answer, which is, I would say it's the wrong answer, but it's not the preferred answer. Because you're going to take the Fourier transform of this and then convolve with the Fourier transform of this cone function. However, if you notice that since this is a limited pulse, all right, basically you have this pulse here. This is your signal. 1, 2, 3, 2, 3, 1, 2, 3. All right, then 1 and 2. So this is your signal here right now. Okay, this goes here up to here, and then you go up to here, and then come down. This is your signal, and then your sampling function is every 2 seconds. This is a sampling function here. Every 2 seconds. So here you got a delta, here you got a delta, here you got a delta, here you get delta. When you multiply these two together, what will you get? You will only get 3 pulses inside here, right? Because everything less than minus 3 is 0, greater than plus 3 is also 0. So what you will get is just 3 pulses. This pulse, and this pulse. Now we've seen a similar question like this in the tutorial. Same question. Tutorial 4, question 1. You've seen a similar question. All right. So whenever you see a pulse that is being sampled, you're going to get a limited number of pulses, that's all. So you only have 3 pulses here. All right. So now if you notice that it has only 3 pulses, when you do the Fourier transform, you'll get a different answer. And that is the preferred answer. Okay. So in this case, you will see that XS are these 3 pulses. All right. You have this at -2 of height 1. So this is delta T plus 2. That is the first guy. The second guy is of height 2, 2 delta T. And the third guy is this guy on the T equals to 2. Again, delta T minus 2. This is what you have of the sample signal. So now if you take the Fourier transform, delta, when you take a Fourier transform, become 1. Shift in time, you have an exponent term. So basically, you have 3 exponent terms. Okay, so if you do that, then your XF, the first guy will be e to the j2 pi f times 2. That's the first guy. The second guy will be just plus e to the 2e to the sorry, just 2 because no shift here. The second guy got no shift. And the third one will be e to minus j2 pi 2. So 3 guys. Now you can leave it as this, or you can combine the 2 with the exponents into a cosine. Either way is fine, but you can leave it as this. Any questions? All right. Okay, then if no question, we move on to the next signals, which is over here. All right. A periodic signal is modeled as follows, where the asterisk denotes convolution. So you have a sin squared convolved with the cone function, sin squared. That means you're doing replication of the sin squared at 0.5, 2 times 0.5, 0.25, 2 times 0.25, 3 times 0.25. And so you're replicating the sin squared term. Okay. So if you're replicating the sin squared term is actually the basic function, the generating function. Yeah. Right? Because you're replicating it. So what you're doing now is you're actually generating a periodic signal. And what's the period? The period will be this guy, 0.25. That's the period. All right. If that's the period, if T is 0.25, then the fundamental frequency will be the reciprocal of that, 1 over 0.25, which is 4, which is part A. That's the answer to part A. Right? Then he asks you, derive and draw a label sketch of the Fourier transform. All right, so let's do that.
Prof.
Yeah.
The period, isn't it, should include the end also? No.
No, that's where it repeats.
Oh, okay. Yes, thank you.
Now, we've seen this many times. In the last 3 weeks, we have been doing this problem, similar problem, every lesson, right? Every lesson. Periodic signal is a generating function convolved with the cone function. And in many of my derivations, I didn't use n, I use k, right? But we have seen it every time. So you can expect that there will be a problem that will require you to look at solving this based on a generating function convolved with a cone function. All right. So you notice in many cases, the questions is testing you over and over again about the use of the replication property of the impulse function. Right? Okay. Yeah. So this is what we have here. All right. So let's look at what the Fourier transform is. Okay, so let's write it down first. So we're told that xt is 16 sin squared 16t convolved with n delta t minus 0.25n. So in the frequency domain, xf will be 16 over 16, it will be just 1. Sin squared will give me a trie, and I get f over 16. Multiplied by the Fourier transform of this will be 1 over 0.25 summation n delta f minus n over 0.25. All right, okay, so I can express n over 0.25 will be 4n. So 1 over 0.25 is 4. So it's 4 try f over 16 times summation n delta f minus 4n. Now let's see what is happening here. We're supposed to draw this spectrum. Okay, so we have a trie of height 4. And it goes from minus 16 to plus 16. That we have a trie. Okay, and you have deltas that are 4 hertz apart. So it will be at 0, at 4, at 8, 12, at 16, etc. Yeah. So you're multiplying those two together. All right, so let's draw it out. Let's say 4, 8, 12, 16. So this is in F, 4, 8, 12, 16. So the first guy is this trie. This is 4. This is the trie. The second one is the comb function. So the comb function is as follows. All right, 4, 8, 12, 16, 4, 8, 12, 16. So you have a comb function here. This is your delta. Okay, so you're multiplying these two guys. So if you multiply these two guys, what will happen? Anything less than minus 16 is 0. To the left of minus 16 is 0. To the right of plus 16 is 0. So all you're left with are these delta functions. 1, 2, 3, 4, 5, 6, 7 delta functions. Okay, this is what you're left with. Of course, you can also calculate what is the height of each. In fact, this is 43210. Okay, if you draw it to scale, the height of each 43210. So that's part B. Any questions? All right, then it comes to part C. Based on the results in part B or otherwise, express xt without using the convolution. Right now it's using the convolution, as you can see here. Right? Express xt without using the convolution. Right? So we notice that xf here is only made out of 7 delta pulses. 7 delta pulses. So if you do the inverse Laplace transform, each of the delta pulses will result in an exponent term because of the shift. Right? And if that's the case, when you do the inverse Fourier transform, there is no convolution operator anymore. All right, so let's write it down. So that means our xf consists of these 7 guys. Okay, so xf going from left to right. Yeah, so this is at minus 12, minus 8, minus 4. So this is of height 1. Delta f minus 12 plus 2 delta f minus 8 plus 3 delta f minus 4 plus 4 delta f Then the next one will be at 4 plus 3 delta F. Sorry, this is all plus going on the left side. Delta F minus 4 plus 2 delta F minus 8 plus delta F minus 12. So these are the 7 guys. So if you take the inverse Fourier transform, delta gives you a 1. Shift will give you an exponent term. So your xt will be, this first guy will be E. Hang on, let me take my call first. Okay, let me continue. So this one will be E to the J 2 pi 12 T. That's the first guy. The second guy will be 2 E to the J 2 pi 8 T. Third one will be 3 E to the J 2 pi 4 T. Then this is just 4. Then the next one will be 3 E to the J minus J now 2 pi 4T plus 2 E to the J minus J, 2 pi 8T. And the last one is E to the minus J 2 pi. Of course, in this case will be 12. So these are the, so you can see now xt has no convolution operator inside. Again, if you want, you can clean it up now, because there are pairs of exponents here that can be converted into a cosine, but not absolutely necessary, which is fine. Any questions? All right, so that's part C. All right, then we go to part D. Suppose we pass xt through a low pass filter to produce the output yt. If the frequency response of the filter HF is rect f over 12, that means you have a low pass filter, all right, and the cutoff frequency is at 12. Sorry, at 6, because if you draw the rect with 12, it will go from -6 to +6, so that's 12. Okay. All right, so in other words, if you draw HF will look like that. This is HF. This is HF. So you see it's a low pass filter with a cutoff frequency of 6, because the width of the rect is 12. All right, so it says find the ratio of the power of the average power of y over the average power of x. Okay, so let's do x first. X has 7 delta pulses here, as you can see. Here you got XF. XF is here. Okay, so the power of x will be the square of each of these. All right, there are 7 of them. So it would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared. That's what this guy is. Okay, and if you work it out, it's 44. Now, what about y? Y is going to be low pass filtered by this HF, which means that for y, you are going to do this. You're going to low pass at 6. So this is my low pass here, up to 6. Right? You're going to low pass there. So if you low pass that, you're only left with 3 delta pulses, because anything above 6 is cancelled. Anything less than -6 is cancelled, because you're multiplying by HF. So in fact, y only has 3 terms. Yt only has 3 terms, which is this term, 3 delta at f plus 4 plus 4 delta F plus 3 delta F minus 4. So the average, oh, so this is F, YF. So the power of Y will be just only this 3 term, 3 squared plus 4 squared plus 3 squared. And that will give you 34. So now if you want PY over PX, it will be 34 over 44. All right, which is 0.77. Okay, so that's part D. Any questions? All right, if not, we move to the next one. All right, question 7. So consider the signal xt given by that expression. Obtain the Fourier transform. Okay, right? So what we can see is that xt is 5 bracket 1 plus cos multiplied by a rect. So multiplication here becomes a convolution. 1 becomes a delta, cos becomes 2 deltas, rect becomes a sinc. So you're going to convolve a sinc with altogether 3 deltas inside here. 3 deltas. Okay, as a repeat, 1 becomes a delta when you do the Fourier transform. Cosine becomes 2 deltas. Rect becomes a sinc. All right, so that's basically it. So you have a sinc that is going to be convolved with 3 deltas, which means that you're going to move the sinc to where these 3 deltas are. All right, okay, so that's question 7. Part A. So let's do it. So let's write it down. We have xt is equals to 5 into 1 plus cos 10 pi t rect of t over 2. So xf in that case will be the 5 is still here. This delta 1 becomes delta f. This cosine becomes 2 deltas, 2 half into. So the frequency here is 5 hertz because 10 pi t. So f will be 5. Delta f minus 5 plus delta f plus 5. Multiplication becomes convolution. Fourier transform of the rect becomes 2 sinc 2f. Okay, so you can see the 3 delta functions now. All right, and then 2 times 5 becomes 10. All right, so now you're going to convolve it. That means you move the sinc to these 3 locations. So you glue that, you get this times this will be 10. Sinc, that's the first guy, 2f. All right, the next one is 10 over 2 because of the half. 10 over 2 will be 5. Sinc of 2. Wherever you see f will change to f minus 5 here and f plus 5. 2 into f minus 5 for this guy and 5 sinc 2 into f plus 5. Okay, so that's your xf. Any questions? All right, 3.6. So now he says, determine the energy spectral density of X and sketch it. So he hints, assume that the overlapping functions beyond the 4th null can be neglected. So we know that XF, EXF is mod XF squared. So you got to square all this. All right, you got to square all this. So you square it, you got 3 terms, you will end up with quite a few terms, huh? All right, because you have all the cross products as well. Okay, all the cross products. All right, of course, you have this squared plus this squared plus this squared, then this times this times this times this, etc. All right, so altogether, you will end up with 1, 2, 3, what is it now? 1, 2, 3, 4, 5, 6 terms. But it's saying that the hint assumes that the overlapping beyond the 4th can be neglected. So in other words, it's saying, don't worry about the overlapping parts, the cross product. Okay, because when you do this, this is actually the first guy squared. So this will be 100 sin squared 2f. The second guy squared, 25 sin squared into 2 into f minus 5. The third guy is this guy, 25 sin squared 2 into f plus 5. And the cross products. So this times this will give you 50 sin 2f sin 2 into f minus 5. So this is this cross product. The next cross product is between the first one and the third one. Again, 50 sin 2f sin 2 into f plus 5. And then the last one will be the second and the third term, plus 25 sin 2 into f minus 5 sin 2 into f plus 5. All right, but it says ignore the cross product. So if I ignore the cross product, I can remove these guys, these 3 guys. Okay, I can ignore that. So I'm just left with these 3 terms. So basically it's a sin squared term, sin squared term. The one in the middle, which is sin squared at 2f, sin squared at 2f. The one in the middle is a height of 100. The left, and sorry, this one is on the positive 5 hertz. This is on the negative 5 hertz. All right, positive 5 hertz and negative 5 hertz will be of height 25. So if you do that, then if you draw the spectrum, basically, so this is EXF. So basically, you will have the following, that imagine you have a sink here, all right? So this is at 100, then you have one at 5 and one at minus 5. Again, here will be smaller. This will be smaller. All right, and this is at 25. This is what you have. The cross products are actually in between here, in between, but it says ignore it. Okay, ignore it. Any questions?
Prof, could you explain the meaning of overlapping?
Yeah, overlapping is this cross products here.
That means
because when you multiply, this goes to infinity, right? Each of the sin go to infinity, right? So this is a product of a sink centered at 0 with a sink centered at 5. Sink centered at 0, 0. So there is going to be overlapping of these 2 sinks, right? In between here, which is this product here, the first term here. You have a sink at 0 and a sink at 5. Sink at 0, sink at 5. Still cannot see.
cannot.
Sink at 0, this guy will continue on to infinity. Sink at 5, let me draw in a different color. Sink at 5 here. So you see where the overlaps are? The blue, the purple and the brown.
Okay.
So where they overlap, all this overlap here is this term here.
Okay, so assume there's no hint. That means if I square the whole function.
But there is a hint.
Correct. If I square
Otherwise,
the
you have to take into considering all these 6 items here.
Okay, I understand. But what I mean is that if I don't have the hint, if I take the square of the function, total I have 9 terms, right?
6 terms. We got 9 terms.
9 terms, right? Because each one inside got.
No. 1, 2, 3, 4, 5, 6 terms. We got 9 terms.
If I 10 sing plus 5 sing plus 5 sing multiply myself, I got 9 terms, right?
We got 9 terms.
Huh?
Come on, this is basic maths. A plus B plus C times squared is A squared plus B squared plus C squared plus AB plus AC plus BC. Only 6 terms, what? We got 9 terms. Where do you get your 9 terms? This is basic maths. There, those are my 6 terms. A is this, B is this, C is this. Where do you get your extra 3 terms? Do you see or not? Is it A plus B plus C squared, A squared, B squared plus C squared, AB plus AC plus BC? All right. 6 terms only. Where you got 9 terms? Okay. What is, it should be 2 right here. Because there's A times B and there's B times A. So I should multiply by 2 for the last 3 terms.
So yeah, so
Where got 9 terms?
yeah, so there's two there, right?
Yeah.
So I mean, if you count individual term, not you expand out, there's total 9 term, but because there's similar, so there's 2, you could add up the 2 terms together. So
yeah, of
so
course you
yeah,
have to add them together because
so-
A times B that repeat itself. What?
okay, so you are saying that the overlapping means the A times B, A times C.
So he's saying that this whole thing here, the hint says that you can ignore this part, which is what we've done.
Yeah, that's why I'm trying to understand the overlapping meaning of this overlapping. So the overlapping means your A the term multiplied by itself. I mean by another term, right? And because when you multiply you look at you draw
So
it out.
theoretically, you have all these things are overlapping, the same overlapping. The question is saying that beyond the 4th null, you can ignore it. So if you were going to draw it, you only draw up to the 4th null for each of these things. That's it. Which means that after the 4th null is 0. Otherwise, you have to draw all these squiggles inside here. All right. So each of these, you only do up to the 4th null. Do you understand?
Okay, so for now is like each sing function, right? The wave after the 4th one we consider as 0,
So
right?
suppose this is the 4th null here for this guy. Anything beyond that is 0 up to the 4th null here. Anything beyond that is 0. That's what it's saying.
Okay. So
okay, which means also that we can ignore the cross product here, because the cross product is all the things that are very small in between the sing functions. I don't think we can finish this paper today in 1.5 hours at this rate. It's okay, never mind. We do go slow. Still don't get it. Yes or no?
need time to digest a bit.
Look here. If you were to plot this graph out, you are going to have little humps all in between here, correct? Everywhere there will be little humps, getting smaller and smaller, right?
Yes.
Correct or not?
Yes, it's a merging of the.
Yeah, that's what I
and
mean by overlap. They're merging.
So it's the middle part where they merge together after.
They are merging everywhere.
Oh.
Because each of these things goes from minus infinity to plus infinity. But it becomes smaller and smaller the further away from the center, right?
Okay.
They are merging everywhere. But the question is
Okay.
saying, ignore anything beyond the fourth now.
Okay.
Okay? So that's why I draw the green lines there. Suppose the green line is where the fourth null is. Then you can ignore anything beyond the fourth null on the right and beyond the fourth null on the left. So instead of squiggles here, it becomes flat now.
Okay.
That's what it's saying.
So that means, but you take away the whole function because
Because it's going to be very small.
Everywhere, because if you take the rest of the formula, the function, everywhere will be overlapping. So that's why you can consider the whole thing is gone. Is that?
Yes.
Okay.
I mean, you can plot this out, no problem. You can use MATLAB. You know, you take this entire expression with six components there. Take MATLAB or you take Excel, you can plot this thing out. And you see in between the three peaks, there will be all these smaller humps. All right, but beyond the fourth one, you say, okay, ignore it. So basically, we're only dealing with the central part up to the fourth null of each of these things. Of course, it's squared now. Okay, and then you magnitude it. When you square, of course, you magnitude it. Are we okay to proceed now?
Yes.
All right. So now he asks you to find the energy. Okay, find the energy. All right, so if you look at this, obviously it is easier to find the energy in the time domain because you've got nice clean signal. DC shifted cos multiplied by a rect. That would be easier to calculate than to try to find the energy with this term. 6 terms here, right? Okay, so obviously it's better to find it in the time domain. So the energy will be integral from minus infinity to plus infinity of 5 of 1 plus cos 10 pi t rect of t over 2 whole thing squared dt. All right, so now it's just maths. All right, now look at this. This is 1 plus cos 10 pi t rect t over 2. So whatever is the cosine wave, the DC shifted cosine wave, you multiply with a rect of width 2. Then that means the rect is from -1 to +1, right? -1 to +1, which means anything less than -1 is 0. Anything greater than 1 is 0. So I don't have to integrate from minus infinity to plus infinity. I only need to integrate from -1 to 1 because everything beyond that -1 to +1 due to the rect is zeroed out. So this becomes, if I square it, 25 into 1 plus cos 10 pi t squared dt. This is just maths now. All right, so here if you expand the bracket term, cos, there's another term here. You will get 3 terms, 1 plus 2 cos plus cos squared. All right, you get 3 terms here. -1 to 1, 25, 1 plus 2 cosine 10 pi t plus cos squared 10 pi t dt. All right, of course, then you have to expand your cos squared into half into 1, cos squared theta into half into 1 plus cos 2 theta. All right, so altogether, you will have 4 terms, each of which you can integrate separately. No? All right, you can integrate it. So I won't go through all the details. You can work that out if you want to. Essentially, if you work it out, your answer will be 75. Because that's the maths part. That's just the maths part. Okay? All right, then we come to D. All right, the signal XT is applied to an ideal low-pass filter with a frequency response of HF rec f over 5. That means you have a filter of width 5. That means from minus 2.5 to plus 2.5. So that means this low-pass filter has a cutoff frequency of 2.5 hertz because the width of the rec is 5. Okay, determine the spectrum of the output from the filter and comment on the shape. So remember, this is your X spectrum over here. It comprises 3 sinks. One centered at 0, one at plus 5, and one at minus 5. Now you say, I'm going to pass this signal through a low pass filter with a cutoff frequency of 2.5 hertz. What does that mean? That means the one at plus 5 and minus 5 will be removed, right? Will be removed, right? So you're only left with the guy in the center, here. That's what happens. Okay? So you're left with the guy in the center, that's it. And what is that? That is just a sink. So if you inverse Fourier transform that, a sink will give you a rect. Correct? Okay? So in other words, if I was to low pass filter this guy, let me use another, I don't have any other color. Okay, I have this color. Okay, not this one. Red. Let me take a red. So if I low pass filter at 2.5, I'm only left with this. 2.5 is here. 2.5 is halfway here. So I low pass filter this guy out. I'm left with the sink. I'm left with this guy here. 10 sink to F. That's what I'm left with. Okay? This has been removed. This has been removed. Okay, so I'm only left with this guy after low pass filter. Follow? All right, so the result is that the output, let me call it Z now. So ZT will be just this guy. So if you do the Fourier transform of the inverse Fourier transform of this, will be 10, 5 rec T over 2. This is what you're left with. Because the one at plus and minus 5 hertz, these two sinks have been removed. Okay, so this is your final output. Any questions? How to get 2.5? The low pass filter is described by rect F over 5. What is rect F over 5? Rect F over 5 is this guy of width 5. From minus 2.5 to 2.5. That's the width of 5. Okay? So what's your cutoff frequency here? 2.5. Any other question? All right. If not, we move on to the systems questions now. Okay. Yeah, I don't think we will complete it because I really have to have a hard stop. Hard stop because I have to rush off to another meeting. Okay, the transfer function of a second order LTI is given as follows. Find the poles and zeros of HS. All right, poles and zeros of HS. So that should be straightforward, right? Should be straightforward. All right, so you can see that there's a 0 here. So the root of this obviously is 1. There's a 0 of 1 here. Okay. Over here at the denominator, you got s plus 3 squared plus 16. If you determine the roots of this guy, where does this thing look like? This is like your underdent system, right? Over here. All right. But if you cannot recognize that, of course, you can use your minus b plus or minus square root of b squared minus 4ac over 2a. All right. So you'll find that in both cases here, you will find that the first guy, you have a 0. And that 0 is 1. Okay. And then you have the poles. All right. So if you recognize that this is, looks like you're under dam, if you look at your formula sheet, now here. You see this guy here? You notice the pattern here? Right? S plus something whole to squared plus another constant. And what are your poles in that case? Minus sigma plus or minus j omega d. Those are your poles. So it's minus of this value plus or minus j of this value. Okay, so you don't even have to calculate it out if you recognize that. Okay, so we are going to take that approach. So if you look at the thing, it will be minus of 3. S will be minus 3 plus or minus j of 4. Those are your poles. Okay. Right. Part B. Find the DC gain of the system. Hence or otherwise determine the steady state output if the system input is 5 UT. All right. What's the steady state gain? G naught, right? Or in this case, H naught. H naught. Right? Okay, so let's oh, what's my question? Yeah. Right? So the gain will be equals to H naught. So you substitute it inside, you get 1 over 9 plus 1. 9 plus 16. That's your steady state gain. All right. Then you have an input. All right. An input of 5 UT. 5 UT. This is your gain. All right. 5 UT. This is your gain. If this is your gain of this system, you input 5. What will come out? The steady state will be 5 times this gain, right? So the output will be, input was 5 times the gain is 1 over 25. So it will give you 1 over 5 UT. Okay. Am I correct? Yeah. Okay. 1 over 5. The output will be 1 over 5. So that's the steady state. Because your input is 5. The system has a gain of 1 over 25. So the steady state will be the product of those two. So that's part B. And finally, we come to part C. Let HT be the inverse Laplace transform of capital H. Derive HT. In the present context, what is HT called? That one is simple lah. Huh? All right. So if you take the inverse Laplace transform of the transfer function HS, HT is actually the impulse response. Okay, the impulse response, because the input will be a delta input response. So the second part of this question is straightforward. It's the impulse response. Okay, so now we have to derive HT. All right, to derive HT, then you have to work it out. All right, as appropriate lah, huh? So what we'll do is we will rewrite this in a certain way. So we are told that HS is minus S plus 1 over S plus 3 squared plus 16. Okay, plus 16. So usual again lah. A1 over S plus 3 squared plus 16 plus A2 into S plus 3 over S plus 3 squared plus 16. You know the usual, you go through this exercise, find capital A1, capital A2. All right, now I won't go through all the details, but we solve for A1 and A2. If you do that, you'll find that A1 is 4 and A2 will be minus 1. So now we have HS is 4 over S plus 3 squared plus 16 minus S plus 3 over S plus 3 squared plus 16. All right. So if you take the inverse Laplace transform, HT will be, so you can see that the first one is a sine with a shift. The shift of S will give you an exponential term. So you'll be sine of 4t with the exponent e to the minus 3t. The second term is a cosine, again with the shift. Cosine 4t e to the minus 3t. Okay, so that is HT. Any questions? Can repeat how you come about that it is an impulse. That's the definition. When you apply an impulse, all right, your output signal is the inverse Laplace transform of the transfer function. Remember, we did this whole thing on input as impulse, input as step, input as sinusoid. Remember that? So whenever you input as impulse, the output is the inverse Laplace transform of the transfer function. 3 options. What do you mean by 3 options? I'm not sure I understand your question. Yeah, we did all that. What? Chapter 8. We said we were going to look at the response of the system for a first order and a second order. For the first order and the second order, we would apply 3 types of inputs: impulse, step, and sinusoid. Those were the 3 that we examined over 2 lectures. Right? Over 2 lectures. So all of that was done over 2 lectures in chapter 8 and chapter 9. Okay, in chapter 8 and chapter 9. And that's how we came up to this table here. Right? We derive all these things, see? We derive all these things. First order, second for impulse. You see the impulse and step. And for sinusoid, we say we're only interested in the steady state. In the steady state, if you have A sine omega t, it becomes A mod G sine omega t plus angle G. You remember all that? We did all this. Yeah. Okay. All right. So that was yeah.
Hello, Prof.
Yeah.
How we use this this one to have the step response?
There's no step response here.
I mean, if we want to get the step response, how we
Then you
use it?
say then you have to do ys is
Yeah.
hs times xs. Remember?
YS. Oh yeah.
Yeah.
We need to
suppose your output is ys. Okay. We know that hs is ys output over input. So if you want to find step response, all right, that means xs will be 1 over s, right?
Yeah.
Therefore, ys will be hs times 1 over s. Then you solve it. Factorize, find a1, a2, whatever, inverse Laplace. Step is always the same. Okay?
Okay.
All right. Now, if you have impulse, if xt is delta t, which is the question that was asked just now, then xs is just 1. And therefore, ys will be hs times 1. And that's why it's called the impulse response. You see?
Okay. Yeah.
Okay. So again, I like to remind all of you, please go to YouTube and watch all the revision of the key points that I gave you all. All this is mentioned back in the key points again. Okay, can you all do that as part of your revision in preparation for the exam? All right. So that is what we call lesson 24 and lesson 25. Lesson 20.
Prof, check with you for the question 1A, right? So the system is unstable, is it? Because the s equal to 1 is on the right hand side.
No, I don't care. That is a zero. Zero does not affect stability. It's only the poles.
Okay, so based on the pole.
So the poles are all on the left hand side. Yeah, you see here. It's all on the left hand side. -3 plus and minus J4. Zeros does not affect stability. We always talk about the poles. These two poles are on the left hand side. So it's a stable system.
Oh, okay, can. Thanks.
Yeah.
But zero will affect the coefficient of your exponent.
Yeah, but it does not affect stability.
Yeah.
You look at all the notes, it has never said zero has any influence on stability.
The stability is depending on the
poles.
On the power,
the poles, as long as they are on the left-hand side, is stable.
Yeah. Okay.
It's very straightforward. There are no buts about it, no ifs about it, no gray area. Very straightforward.
So if both poles all at the left hand
it's stable,
then it's stable and also bounded.
On the imaginary axis, it's called marginally stable.
So it's also bounded.
Also poles. I don't know where the zeros came in.
I mean the bounded, have bounded, right?
It's from the transfer function.
No, she mean it's bounded.
Yeah, it's bounded.
Yeah, stable means bounded. Output is bounded. That's the definition of stable. That was the first lesson we did after the recess, where we define stability.
So stable and the marginally stable both bounded.
Yeah. Imaginary means it's oscillating. Isn't it bounded? Bounded means finite. All right. Chapter 6. We define systems. Remember, we talk about causal, non-causal, discrete and non-discrete, linear, time invariant, time varying. We describe all these categories, including stability. Remember that?
Yes. So any single one pole is in the positive side, you'll be totally whole system unstable.
Yep.
Okay.
You just need one.
And the result of this is a complex conjugate, meaning that if does it have any meaning? Complex conjugate.
You mean this -3 plus or minus J4?
Yes.
That means you have a stable system. Are they on the left-hand side?
Other than stable system, does it like dam or whatever?
Then you have to look at the whole expression.
So that means now I got to look for the whole expression comparing to k omega n divided by blah 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 blah. Then you
you already derive it down here. You can see that it's oscillating. Of course, this is for the impulse input.
Oscillating.
But it will decay to 0 here. Because the t was infinity, it will go to 0.
Correct. You decay to 0 because of the negative sign of the exponential term, right? The power.
Excuse me, Prof.
Yeah.
For the question 1, part B, the steady state output of the system, shouldn't it be 1/5s?
No, this is in time. It will be 1/5 UT.
Oh, okay. Wait, 5 UT
Yes.
is the input. X.
5 UT is the input. The steady state output will be 1/5 UT.
Okay, got it.
Any other question? Okay, if not, we go to the second systems question, and I think we have to finish there because I got to leave already. Okay, good. I'm glad some of you are asking questions now. At least I know whether you're following or not. Okay, a second order system with input X and output Y is described by the differential equation as shown. Determine transfer function. Okay, straightforward. All of you should be able to do this. Just take the Laplace, right? Okay, that's the first part. So let's just do the first part first. So what do we have here? We have d2 by dt squared yt plus 6d by dt yt plus 25 yt equals to 50 xt. So you take the Laplace. Since you want the transfer function, then initial conditions are all 0. So you get s squared ys plus 6s ys plus 25 ys equals to 50 xs. So you group your ys together, s squared plus 6s plus 25 equals to 50 xs. So your transfer function is ys over xs, which will be 50 over s squared plus 6s plus 25. Okay, straightforward. All right, everyone. Okay. So next, he says, determine the damping ratio and undamped natural frequency. So you compare with this guy, k omega n squared over s squared plus 2 zeta omega ns plus omega n squared. So you can see omega n squared is 25, right? Omega n squared is 25. Therefore, for omega n is 5. Then for zeta, 2 zeta omega n is 6. 2 zeta omega n is 6. So from here, you can see that an omega n is 5. All right. So zeta will be 5 times 2 is 10. So it's 6 over 10, which is 0.6. Okay. And then we, any questions so far? I think that's pretty straightforward, this one. All right. Then we come to the last part. If the input signal xt is 3 sine 6t, derive the steady state. Again, straightforward. Then we have to find what is g j omega first, because we will need mod g and angle g afterwards. So g of j omega is this guy. G of j omega will be 50 over j omega squared plus 6 j omega plus 25, which will work out to be 50 over 25 minus omega squared plus j6 omega. All right, and therefore mod g of j omega will be 50 over square root of real squared and imaginary squared, 25 minus omega squared plus 6 omega squared. So that will be mod g. Similarly, angle g will be angle of 50 is 0, so we can ignore that. Just arctangent minus arctan minus 1 imaginary over real, 6 omega over 25 minus omega squared. So we've derived the expressions for mod g and angle g. So now we are told that the input is 3 sine 6t. That means omega is 6. Okay, omega is 6. All right, so we need to find mod of g j6 and angle of g j6. All right, so we just basically apply inside here. I won't go through all the details. So we need to find mod of g j6 and angle of g. So if you substitute inside, I won't go through the details. If you substitute inside there, you will get 1.38, 1.328. And angle of g j6 will be minus 1.8, minus 1.867 radians. All right, this is what you will have. So now you want to find the steady state. So why steady state? Steady state will be the input. The input is 3 sine t, 3 mod g sine 6t plus angle g. Okay, so if you work that out, 3 times this will be 3.984 sine of 3t minus 1.867. Okay, so these are all very standard stuff that we've done many times before. So this is actually quite a straightforward question. Okay, everyone. Okay, so I will have to stop here for today, because as I said, I have to rush off for another meeting.
Prof, a short question. If a system is stable, the root have to be on the negative side, meaning the polynomial of the expression of a second order, the coefficient all must be positive. Is that a correct statement?
No, the coefficient can be positive, and that's the multiplier for that one.
Yeah,
again,
but
don't you are self-confusing, you know. You're self-confusing. Make it very, very simple already. I already said, whatever it is, you just find the poles. So long as the poles are on the left-hand side, is stable. If it's on the imaginary axis, it's marginally stable. It's a very simple rule. No need to worry about coefficient this on that. No need. Just understand where are the poles. Are they on the left-hand side or not? Are they on the imaginary axis, or are there any pole on the right-hand side of the complex plane? That's the only test for stability.
Yes. So that means for a second order system,
it doesn't care what order, whatever order it is, you still have to find the poles.
Yeah, the pole will end up as let's say, for example, s plus something bracket, then s plus another thing, right? Then,
yeah, so just find the roots, find all the poles.
Correct.
All the poles must be on the left-hand side or on the imaginary axis.
Correct. So let's say for example, s plus a bracket, s plus b bracket, and a must be more than 0, B must be more than 0. Then if I expand out this bracket.
No. Again, when you do that, you remember you factorize it, you have all the subsystems there. Each subsystem will have the pole and 0 there.
Correct.
Yeah, so you have to factorize to see what is the subsystems. What is G1, G2, G3? G1 will have a pole of 0. G2 will have pole of 0. G3 will have pole of 0. Each of them can be mapped into your complex plane.
Correct. I just, I think maybe I rephrase my question now.
Yeah.
So let's say I given a system that is stable, okay, and then
right now we do not know until we check the poles.
Correct. Let's say I'm saying that this system is stable.
Okay.
Derive is denominator.
Yeah, that is not enough information to know what is the denominator.
But
unless I told you what are all the poles.
Correct. Let's say but the basic thing I can derive from this is that because the system is a second order system and the system is stable, I say derive the denominator. Yes, I cannot get the full answer, but I can say that the coefficient are all positive, are more than 0, right?
I don't know what you mean by coefficient here.
That means s something s squared plus something s plus and the constant. Okay, that means the first power of s, the coefficient will be more than 0 and the constant will be more than 0.
You are making life difficult for yourself. Why? Because if you know what are the roots of this expression, the roots which are called the poles,
yes,
the roots will tell you whether it's left hand side or not.
Correct. Now
that's all you need to know. That's all you need to know. Whatever is the coefficient.
I understand. So, but now.
Yeah. So now you're playing with maths on your head. All right. So don't go that path. That's what I'm telling you. Just look at the poles.
Right.
Don't care. Don't make any pre-assumptions about whether the coefficient is positive or negative. Just derive the poles.
Okay.
That's it.
Okay.
You are making assumptions that see whether got a certain pattern about the coefficient. It doesn't matter. So long as I know where the poles are, that is where the answer of stability comes from. That's it.
Okay.
That's all we care about. All right. So that's why whenever we look at a system, we have to factorize it into its basic subsystems. Once you factorize it, you can see all the poles there. And you can see immediately whether all the poles are on the left-hand side of your complex plane or on the imaginary axis, or if there's one naughty guy that's on the right-hand side. It's all there. It's all evident there once you determine the poles. Make no assumptions about coefficient this, coefficient that. It doesn't care what the coefficient is. What it cares is where is the position of your poles in terms of checking for stability. Okay? All right. Okay, then. Yeah, I really got to go. All right. So we will have another session on Thursday. All right. All right. Bye, everyone.